Welcome to this presentation at the virtual IEEE Photonics conference. My name is Niels Quack from EPFL, Lausanne, Switzerland, and it's my great pleasure on behalf of all the co-authors to present our work on scalable NOEMS in Silicon Photonics. So what are NOEMS? NOEMS are nano-opto-electromechanical systems, and you find them today in numerous applications such as sensors and actuators for navigational devices or in, for example, consumer electronics projection systems. And there is a wide variety of sensing systems and actuation systems that are currently used with NOEMS. And integration using micro and nano engineering is really the only solution for such high-performance, scalable, cost-effective systems. So what are Silicon Photonics? Silicon Photonics is the wafer scale photonic integration of passive devices of active components such as modulators and detectors to perform various functions on a single chip. One can also integrate with electronic and integrate sources or optical fibers for the in and output. And today, the majority of these developments are driven in photonics integration for tele and datacom applications, such as this high-speed photonic integrated transceiver. Yet there is a huge potential for using these technologies, for example, for on-chip optical communication, for quantum information processing, quantum key distribution, imaging, quantum sensing, and so forth, or for example, also to enhance computing by using photonic accelerators for artificial intelligence applications. So why would you go for using silicon as a material for photonics? Well, in one short answer, one wants to leverage the legacy of the semiconductor industry. And this means one can use the design and fab environment that can drive the low-cost applications. One can achieve the reliability and low-power performance that is required for such systems. And also one can achieve the integration yield that is required to scale to large systems. One can integrate the electronics on the same substrate or co-integrate. And all this together provides the models for access through foundry models that then can standardize the access to this high performance technology. This allows them to scale up circuits to very large scale integration in photonic integrated circuits. So what can this be used for? So I want to highlight here one concept for such very large scale integration in PICs. These are all-purpose photonic integrated circuits. For such circuits, one is required to have thousands to millions of photonic gates on a chip that then can be reconfigured to address specific functions on a on the chip to reprogram basically the overall function of this photonic integrated circuit. So for this, one needs to package the chip to the outside world with the electronic and the optical interfaces, and one needs to have a programming interface. So this can be viewed in the review article from Professor Bogertz and co-authors. And what is required for such a all-purpose photonic integrated circuits, it's a really large number of optical gates, and these optical gates consist in phase shifters and tunable power couplers. And for a similar concept such as the FPGA in electronics, to achieve that in photonics, one requires typically tens or hundreds or millions, tens or hundreds of thousands up to millions of photonic components on a single chip. So how can one achieve the scalability to such very large scale integrated photonic integrated circuits? So in essence, it is a finite resources problem. So the resources that are limited on a photonic integrated circuit are the chip size, the optical power, the optical spectrum, and the power dissipation. One additional resource that is always limited, of course, is time, but I will take that separately because this depends on the application that is required. So what does it mean on the devices in a certain technology? So the chip size dictates that one needs to decrease the footprint of each individual device. One needs to decrease the optical losses of each individual device, and one needs to increase the spectral response to support a broad optical spectrum. The power consumption of this device needs to be low, and depending on the application, it should of course also have a fast response time. So how can one address these items at the same time? So of course the physical effect will dictate the losses, the footprint, and so forth, but one has also the opportunity to influence, for example, the spectral response with the required design. Fabrication and the technology, of course, they play a large role in addressing these requirements, and the architecture can also provide avenues to address these. On the system level, then, one needs to think about the optical in and output and the electrical in and output. And if we scale to very large-scale integrated systems, then we see that we need to increase in these. And in order to address the system requirements, so technologies are being developed to use fiber arrays, thin fibers, multi-core fibers, or also techniques such as photonic wire bonding. For the electrical I/O, so flip chip bonding is typically used, for example, directly integrating CMOS electronics on so by flip chip bonding CMOS onto the photonic chip, or using a redistribution interposer. One can also use wire bonding directly off the chip, typically then using, for example, a row column addressing scheme. Co-integration with CMOS is also possible, of course, which requires adaptation of the technology. So, and for all of this, of course, if you want to go to very large scale integrated photonic integrated circuits, one needs to address the yield, and this is only achievable with standardization of the technology, meaning one can resort to computer-aided design tools and have the fabrication under control. So this brings me now to scalable NOEMS in silicon photonics. So let's look at these device requirements. So I would argue that the spectral response and the response time, so these have to be looked at apart, right? So the spectral response can typically be addressed for all of devices by adequate design. And what is interesting, so the response time has been a driver for most of the developments for the optical transceivers today. So if you want to achieve high-speed modulation, then one can use, for example, the free carrier dispersion effect in silicon, or one can go to specific materials that have direct so electro-optic modulation using the Pockels effect. So these are very fast effects, but the magnitude of the effects is actually quite low. And what that resorts to is that for these high-speed devices, one typically needs quite a long device to achieve the required modulation. So interestingly, MEMS, NEMS, they have a very strong effect. So they're maybe not the fastest, one can achieve maybe sub-microsecond types of response time, but nevertheless, the interesting part is that the magnitude, that the effect is very strong. So let me print maybe now the device requirements, footprint, optical loss, and power consumption in a separate graph here. So if you look at the power consumption, we want to reduce this, of course, and the optical loss and the footprint at the same time. So now we see that, for example, electro-optic effect or plasma dispersion effect, so these lead typically to very large devices, and they have a very high optical loss due to the length of the devices. So MEMS, NEMS, the combination of a very strong effect and very short devices makes them actually very attractive for large-scale integrated circuits, and also they can be very low power consumption. So there is kind of a sweet spot for MEMS, which are uniquely suited for large-scale programmable photonic integrated circuits. All right. So what can be done using NOEMS in PICs? So one can use the micromechanics to control the electromagnetic radiation in terms of power, direction, wavelength, the spectrum, but also the beam shape or the pulse shape, the wavefront or the phase. And all this is compatible with the microsystems technology for the fabrication of such devices. So MEMS transducers are really a mature technology. So they're actuators such as electrostatic, electrothermal, piezoelectric, or electromagnetic actuators. And displacements that can be achieved are typically in the range of nanometers to micrometers, but with a very good position control in the range of nanometers. And the speeds can be in the range of better than microseconds even. So in a photonic integrated circuit, one can use such transducers to play on the coupling distance of a coupled waveguide system by displacing waveguides. One can play on the effective index by displacement or by introducing strain. And one can introduce also non-volatile states by exploring latching, for example. For all of these, one requires suspended waveguides and the integration of the transducers in the same technology. And this allows to fabricate nano-optoelectromechanical systems. So what has been implemented so far? There have been mainly two avenues that have been performed. So for example, multi-layer systems using a surface micromachining technique, or single layer devices using the removal of a buried oxide sacrificial layer here. So let's look at surface micromachined silicon photonic MEMS. This is an example of a freestanding waveguide from the work at UC Berkeley that is like suspended at a certain distance from a fixed waveguide here. And on the left-hand side and the right-hand side, you see the suspensions that allow a mechanical movement by electrostatic actuation between these two capacitor plates. So you can now, once you can manufacture these devices, you can also arrange them in such a way in an architecture that allows, for example, to have an adiabatic coupler attached to these actuators here and the suspensions. And by actuating, you can pull this waveguide down and bring this blue top waveguide in close vicinity to this bottom red waveguide, and thus fulfill the coupling condition that allows them to couple the light around the corner and at the same time then back to the bottom waveguide here. So this is a means to redirect the light on chip, and the beauty of the technology is that one can integrate thousands of these on a single chip. So this is a 64 by 64 array on a 7mm by 7mm system that has 4096 individual MEMS switches. The performance of this is excellent. So for the 64 by 64 switch, the maximum is about 4 dB on-chip loss. And it's a very broadband response, and it's also very fast, below 1 microsecond. So this combination of low loss, broadband, compact, and also fast device shows that this is very scalable to large-scale systems. So the challenge of this technology is, of course, one needs to have a dedicated technology to provide these MEMS. Nevertheless, there have been many demonstrations over the past years, including wavelength selective switches, digital phase shifters, non-volatile photonics, and so forth. And this is, of course, a very promising technology. So if one wants to go to a more standardized type of platform, where standard silicon photonics is using, so then one wants to use single layer silicon photonics. And this provides an access to high quality standard components and the co-integration of the most advanced and highly reliable technology platforms that are available today. And this will then enable the large-scale integration. So here is an example from our colleagues at the GIST that use, for example, a single layer of silicon with a evaporated chrome gold layer, and the intrinsic stress upon the position leads to a displacement of the waveguide to uncoupled position here. So now one can use the application of an electrostatic force here by applying an actuation voltage between this movable waveguide and the fixed substrate, and the waveguide then can bend down and fulfill the coupling condition between the waveguides. So the advantage is really that this is quite straightforward to integrate in a fabrication process. And the group has this year at CLIO presented how you can actually implement a programmable mesh with 16 cores to fulfill this function for programmable photonics. So we have pursued a different route. So in our case, we use standard Silicon Photonic, and we enhance this platform with MEMS technology. So we work on the optimization of the design of these NOEMS. We develop the process and the full integration in a standard platform. So depicted here is the cross-section of a standard platform, and it consists of IMEC IC50G standard components such as the germanium photodetectors, copper interconnect layers on several layers, high efficiency grading couplers, high speed modulators, and bond pads to connect to the outside world. So this is the standard platform at IMEC, and we at EPFL have developed a post-processing process that allows to selectively remove the buried oxide and protect the MEMS here selectively to produce freestanding photonic MEMS structures. Our colleagues at KTH, they work on a wafer level hermetic MEMS sealing process, and by providing lids selectively over the MEMS structures allows a long-term reliability of the MEMS structures by still providing the access to the optical and electrical interfaces. So let me show a few examples. So this is a first example, a continuously tunable 2x2 power coupler, and we see here the components of the standard platform, and we have included optical transitions to interface with the standard components. So here we have a fixed waveguide, and we have a movable waveguide that is attached to an electrostatic comp drive actuator. And in the idle state, the light is being coupled to the drop port. Now, once we apply an electrostatic force, so by applying a voltage between the fixed part and the movable part here, we move the waveguide away from the waveguide, the fixed waveguide here. And now the light travels from the input port to this through port. So we have here an in-plane movable coupler that can be actuated by the comp drive actuator. So this is a scanning electron microscope recording that shows the well-suspended coupler here above the handle layer, the freestanding waveguides, and the optical transitions. And you can distinguish the well-defined comp drive actuators and the electrical isolation between the ground and the voltage actuation pads. So here is the input port, and here is the drop port and the through port to the right. So the nice thing about this technology is that one can integrate now all high performance components next to our MEMS component here. So it's a MEMS cavity here, and we have metal routing, waveguides, contact pads, grading couplers, where we can then interface the input, through port, and drop port to the outside world. So we test these devices using a fiber array and the electrical probes for the electrostatic MEMS actuation and the tunable laser to record the spectrum. So you see here on the left-hand side the tuning of the laser, and we record the spectrum at the drop and the through port. Now we actuate the MEMS, and for different MEMS position, for a movable waveguide position, we record the spectrum. So the combined response is shown here on the right-hand side, and we see that we get an excellent extinction ratio of about 27 dB over an optical bandwidth of about 30 nanometer with quite low actuation voltage. And together with a compact footprint and the low loss that these devices exhibit, again, we demonstrate that these are excellent candidates for scalable systems. So let me show a second device. So this is a digital 1x2 silicon photonic MEMS switch. So in the idle state, so the input here is actually not coupled to the two outputs 1 and 2, which is shown here to the right-hand side. However, when we apply a voltage to this electrode here, then the shuttle is being displaced towards the top here, and the two waveguides are being now coupled from the input to the output 1, which is shown in the FDTD simulation here to the right-hand side. The fabricated device under a scanning electron microscope shows excellent defined structures, the electrodes on the left and right side, the stoppers here, the anchors, and we have the output 1 and 2 here. And again, we see that we have the integration of our MEMS next to all the standard components of the advanced platform of IMEC. It's also very compact, as we can see. So this square for reference is 50 by 100 micron. For the optical performance, so in the idle state, we don't couple in gray here. And then when we switch the electrode 1 on, then we have all the power coupled to the output port 1, no power in output port 2. And inversely, once we couple to port 2, then we have all the power in port 2 and no power in port 1. So for the combined response here, so we see once we actuate the electrode 1, so we increase the coupling to the output 1, and the output 2 has almost no power. We get excellent extinction ratio and the same behavior on the electrode 2. So it's a very fast response. So here, due to the compact design, we have less than a microsecond response time. And this leads to very compact and low loss devices with high extinction ratio, and again, very broadband due to the design of this adiabatic transition. Again, very scalable component. The next component has been developed by our colleagues at KTH, and it shows a phase shifter that is very low loss and can be actuated by MEMS. So we have the input here on the left-hand side, the light travels through the waveguide here, and we have a MEMS actuator here that is connected to a phase element here. And we can actuate the MEMS and induce a displacement and thus change the gap between the waveguide and the phase element here. So let me show the cross section here on the right-hand side of this element. So most of the power is coupled in the waveguide. However, there is a residual part that is being coupled to this phase element. And upon displacement of this phase element, we change the effective index of the coupled waveguide system. And by doing so, the phase that is being accumulated over the distance in this waveguide actually changes. And this is shown here. So the actuation from 0 to 36 volt shows the response of the phase shifter here. And if you calculate the accumulated phase, you can see that we can accumulate more than 2 pi phase shift with 36 volt of actuation voltage, while keeping the insertion loss of the device less than half a dB. So again, we have a very compact device. We can achieve 2 pi phase shift, and we have a low insertion loss. It's fast, so the resonance frequency of this device was about 0.5 megahertz. So in summary, for these devices, we have shown now 3 examples of a digital 1x2 switch, a 2x2 analog coupler, and an analog phase shifter. For all of these devices, they're low loss, they're low power consumption, they are very broadband and very compact, and this combination makes them scalable to large-scale photonic integrated circuits. They're also very fast in the microsecond response time region. So next, our colleagues at KTH, they work on a wafer-level photonic MEMS sealing process. And for this, the aluminum of the bond pad is being used, and it's being designed as an aluminum bond ring next to all the standard components of the platform, and of course around our MEMS devices of our technology. So the wafer level sealing process uses a gold aluminum thermocompression bonding, and this is full on wafer level, but allows to place silicon lids on the places where there are our MEMS devices. So this provides hermetic silicon photonic MEMS sealing, and the height of these lids is in the range of about 20 micrometers, and this provides a long-term reliability for the NOEMS. So the height is very important, actually, that this is a very low height of 20 microns. As we can see, we can now actually flip chip bond this to a glass interposer by using this bond band distributed on the photonic MEMS chip. And we use here, for example, a glass interposer that allows then also to integrate the fiber arrays here on the left-hand side and flip chip bond the whole system to a printed circuit board and wire bond these contacts here on the edges to the printed circuit board. So again, so the sealing process on wafer level is compatible with this glass interposers for flip chip packaging. So this is a similar approach that has been shown, for example, for flip chip bonding to ceramic interposer, also silicon interposers, or one can also think about direct wire bonding, which has shown previously using row column addressing. So this approach allows to pull out a certain number, maybe a few hundreds of contacts, but this can also be standardized to very large scale interposers. In addition, what can also be done, of course, is flip chipping electronic integrated circuits. So this is already available for standard type of silicon photonics, and this can be expanded for MEMS as well. The challenge is here to integrate the rather high driving voltages, but of course, this can be pursued as well. So let's look at the standardized very large scale interposer. This is pursued in MORPHIC by our partners at Tyndall. And it allows, in this particular design, to pull out thousands of transmission lines and redistribute them to connectors on the bottom side of these interposers. So this uses 20 layers in Kyocera's high-tech ceramic interposer technology. And you see here now the large-scale photonic IC that can be flip chip bonded onto this very large-scale interposer, and we can pull out thousands of electrical connections to the interfaces. Next to it can also be the electronic ICs for high-speed TIAs, for example. So in summary, I hope I was able to show you how NOEMS can be a candidate to go towards all-purpose photonic integrated circuits using advanced NOEMS technology in standard silicon photonics for reconfigurable photonics, and using flip chip bonding to interposers and the electrical interfaces outside here. So we have demonstrated the technology platform as such, but also that the individual components here, such as the tunable power coupler, the phase shifter, or the digital switch, that these are compact, low loss, broadband, low power, and fast, and that this combination is really the essence of scalability. So from this, we can go from devices towards circuits, integrate the sealing and the interfacing. And this is really a very decisive technology step for future large-scale programmable photonics. So hopefully in the future, we have some photonic programmable circuit that has MORPHIC inside for sensing, for quantum information processing, for artificial intelligence, and so forth. So with this, I would like to thank all the contributors to this presentation, in particular, of course, the MORPHIC team. And we are happy to conclude this presentation at this point here.